I'm going to show you how you can use GeoGebra to perform linear regression and exponential regression. So we're going to use this example here from your homework. We're given a table and we have that X is the age of a driver and then Y is the percentage of fatal accidents of drivers of that age. So for example, if we look at X is 37, that means for the people that they sampled that were 37 years old, 4.19% of them were in a fatal car accident. First, we're going to graph the data, and we're going to do that by going over here to where it has the table. If you have something in there, you can clear it out. So what we're going to do is we're going to put in our X column all of these X values and make sure we're doing it in order so that we pair up our Y's correctly. So we're going to put in 37, then 47, 57, 67, 77, and then 87. So those are all of our X values, the ages of the people that they sampled. Now, for the Y values, what we're going to do is we're going to go back to our algebra option, and I'm going to put in the corresponding values of Y. So I'm going to do Y equals, and then we need to use curly braces to indicate that this is going to be a list. Now, for our Y values, we're going to put in 4.19, comma, then 10.17, comma, 20.4, comma, 26.84, comma, and then 26.7, comma, and 40.63. If you don't have enough room to see it, remember you can pull this bar out so that you can see all your values. I definitely recommend that you double check that you put your values in correctly and that you have the correct number, because if you are missing a Y value or you have an extra Y value, it's not going to line up right with your X's. Now what we're going to do is we're going to tell GeoGebra to put these Y values in the table of values. So now we have it listed here. You can also see that when we did that, it plotted the points for us so that we can see those points. Now, once we see the graph, remember you can click and drag and move it around or zoom in and out until you get the right scale. And once you get the right scale, you go to these three dots over here on the Y values that you're looking at, and you're going to hit this option here, regression. You're going to have different options here, so make sure you're picking the correct option. We want a linear function. So I'm going to make sure that I'm on linear, and then it's going to calculate the line for me. So here's our formula for the line. It's giving us our value of A and our value of B. So when I put my answer in, if I need to enter in my regression line, I would put in, let's say we're told to round to two places. So I would put in for A, 0.68, and then for B, I would put in negative 20.71. So my equation that I would enter in for my answer would be Y equals 0.68x plus negative 20.71. That would be our line. Here's our coefficient of determination, and here's our correlation coefficient. Notice that this is pretty close to 1, and R is positive, so that means it's going to have a positive slope, and it's really close to 1, so this is going to be a really good model. This line is going to come really close to all the points, but not exactly. And then I'm going to click on plot, and see this line comes up through these points pretty close, so this is a really good model. Now, if we want to see what happens in between these points, if we want to estimate, because these are the only data values we collected from our sample, so we can use the line to estimate the values in between. So if I wanted to find the approximation of fatal accidents for someone that's 40, I could use that line and plug in 40 for X, and I could get my estimation. So that's how you use linear regression. Now, if you want to use exponential regression, you go through the same exact process, but you would just choose this option here. For exponential models, we have this formula. We have our initial value that's in front. Then we have our natural constant raised to some power. You could have a coefficient times x. So b would be your coefficient in front of the x that's within the exponent. So GeoGebra supplies those values for us because it did the arithmetic in the background. So our initial value, if we round to 2 places, I would put in 1.31 for a. Then I would multiply by the natural constant raised to the power of bx. Since b is given as 0.0415, we would round to 2 places to be consistent, and I would put in up here 0.04 times x. So that would be our formula if we're looking at an exponential function. Now there's a different form of the exponential function. This is the form where you have the natural constant here. There's another form that you can use. It just depends on what the question asks. And both of them will give you the same answer. It's just a different way to write it. So if you're asked to use the formula with the base e, you want to use exponential. If you want to use the formula where your b is not the natural constant, where you could have any constant here, if you have this form where you have the initial value times b to the x, then you would use this growth model here. So for this one, I would have 1.31 in front here times b, which is 1.04 raised to the power of x. And then if you want to see it again, you can plot it, and it will change the function. Now you notice that in this case, the exponential function doesn't fit as well. It's okay, but the linear function fixed the points a lot better. So this is what you want to do to come up with your models. Once you have your model set up, then you can use that to estimate between the data values or a little bit past. You don't want to go out too far in either direction because usually these models only fit over a certain range of values. We don't want to go too far out in either direction. We want to stay close to the data.